Let's work on the problem 8.8.21. We need to find eigenvalues and eigenvectors. First, eigenvalues. How we find the eigenvalues? Determinant of matrix A minus lambda I. We're going to let that equal to 0. Basically, we need to find the delta of this matrix and let that equals to 0. Find the lambda. So that is A minus lambda. So diagonal way, I'm going to subtract minus lambda, 5 minus lambda, negative 7 minus lambda, and all others can just keep it. To find the determinant of the matrix, what we did in class, we're going to copy down top 2 rows in here.
Then we have 1 minus lambda, 2 and 3, 0, 5 minus lambda and 6.
And we're going to look at the diagonal way. So here, and this is 0. We don't have to worry about. This is 0. And for opposite way, this is 0. This is 0. This is 0. All negative of that. Therefore, we have 1 minus lambda, 5 minus lambda, negative 7 minus lambda. This is the only term which is not equal to 0. So now this term, we're going to let that equals to 0 based on this formula. From here, we don't have to expand it. We just need to find the lambda. So eigenvalue lambda 1 as a 1, eigenvalue lambda 2 as a 5, eigenvalue lambda 3 as negative 7. We have 3 lambdas eigenvalues, so we need to find 3 eigenvectors. How you find the eigenvectors? What we're going to do, we're going to put in A minus lambda times I bar 0. Then use Gauss-Jordan elimination method. We're going to find K1, K2, K3 relationships here. This is A. Now for lambda equals to 1, we need to do A minus lambda I. So in the diagonal way, I'm going to subtract by 1. So 1 minus 1, 0, and the rest is the same. 5 minus 1, 4, 0, 0. Negative 7 minus 1, negative 8, bar 0, 0, 0. For the first column, first row, first column, we need to make 1. However, in this matrix, first column is 0. So we have to make second row, second column, this guy, to be 1. Then we can simply divide by 4. Then we have 0, 1, 3 over 2, bar 0. Now we need to make this guy to be 0. So what we need to do, R2 times negative 2, add R1, put it back to R1. 0, negative 2, negative 3, 0. We have a 0, 2, 3, 0. Give us all 0. So now we have 0, 0, 0, 0. And then this guy, we're going to divide everything by negative 8, 0, 0, 1, 0. We're not done yet, right? So now what we need to do, we need to make this guy to be 0 because we have third row, third column is 1. Therefore, we need to do R3 times negative 3 over 2 and then add R2, put it back to R2. Then we have 0, 0, 1, R3, 0, 0, negative 3 over 2, 0, 0, 1, 3 over 2, 0. So it's going to be 0, 1, 0, 0. First row is all the 0. So that's it. After we finish Gauss-Jordan elimination method, now we're going to write first column as a K1, second column as a K2, third column as a K3. For the first row, everything multiplied by 0, so everything is 0. Now, second row, K1 times 0 is 0, K2 times 1 is K2 equals to 0. And then third, K1 times 0 is 0, K2 times 0 is 0, and then K3 equals to 0. So our first eigenvector equals k2 and k3 is 0, and we can use any number, the first row, first column. I would say 3. So we're done with lambda equals to 1. Now for lambda equals to 5, we need to do a minus lambda I. So again, what we're gonna do, we're gonna a minus lambda. Then we have 1 minus 5, negative 4, and 2 and 3, and 0. 5 minus 5, 0, and 6, we have a 0, and 0, 0, negative 7 minus 7, negative 12, and 0. Now from this, we need to make this guy to be 1. So we want to divide whole row by negative 4. Then we have 1, negative 1 over 2, negative 3 over 4. And then second row, if you divide by 6, we have a 0, 0, 1, 0. Divide by negative 12, 0, 0, 1, 0. Since we don't have second row, second column as a 1, let's make this guy to 0. Can use R3 times 3 over 4, add R1, put it back to R1, we have a 1, negative 1 over 2, 0 and 0, 0, 0, 1, 0, and then R2 times negative 1, add R3, put it back to R3, we end up getting all 0 here. Again, this is K1, K2, K3. Each column represents lowercase 1, 2, and 3. So now when we multiply them, we have K1 minus 1 over 2 K2 equals to 0. And from here, K1 equals 1 over 2 K2. And from here, we know K3 equals to 0. Second eigenvector is going to be, we can just let K2 as any even number. Maybe 10. 10 divided by 2. K1 is going to be 5. And then K3 should be 0. So the last one for our lambda 3 is negative 7. And then I'm going to write a vector again here. Diagonal way, we're going to subtract 7. 1 minus minus 7, which is 8. 2, 3, 0. 5 minus minus 7, 12, 6. And 0, 0, minus 7 minus minus 7, which is 0. And we have a zeros here. So we want to make this to 1. We have a 1, 1 over 4, 3 over 8, and 0. And we want to make this to 1, 0, 1, 1 over 2, 0. And then we need to make this guy to be 0. So what we want to do, R2 times negative 1 over 4 plus R1, put it back to R1. 0, negative 1 over 4, negative 1 over 8, 0. And 1, 1 over 4, 3 over 8, 0. It's going to be 1, 0, 1 over 4, 0. And 0, 1, 1 over 2, 0, 0, 0, 0, 0. Since we don't have 1 in third row, third column, we have to use these. Now K1, K2, lowercase k3. From first equation, we say K1 times 1, which is K1. K2 times 0 is 0, plus 1 over 4 K3 equals to 0. From here, K1 equals the negative 1 over 4 K3. From the second row, we have K1 times 0 is a 0, K2 times 1 is K2, plus 1 over 2 K3, that is 0. From here, we have K2 equals negative 1 over 2 K3. Then our eigenvector, capital K3, is going to be, we can let K3 equals anything multiple of 4. That way we don't have to have any fractions. So you can say negative 8 maybe. So K3 is negative 8. Then K2 is positive 4. K1 equals positive 2. So that's our third eigenvector. So when do we use these eigenvectors? In the future, when you have a control system, we have a matrix, a given system as what? 1, 2, 3, 0, 5, 6, 0, 0, negative 7. That's the given matrix A. It's a given system. And then if we multiply any eigenvector, 2, 4, negative 8, for example, as an input, this is the given system, then see what happened to output. This is 3 by 3, this is 3 by 1. Inner numbers are the same, good. Outer numbers, that's our result. So 2 times 1, 2 plus 8 minus 24, and 0 plus 20 minus 48, 0, 0 plus 56, and that is negative 14, negative 28, positive 56. And if we factor out negative 7, then what happened? We have a 2, 4, negative 8. So this eigenvector is here. So we can produce some gain, positive gain or negative gain. That's how we use these eigenvectors.